Hello everybody. In this video, we will learn about developments after Kepler and Newton that allowed us to better understand complex celestial motions, such as gravitational interactions and resonances. Newton's formulation of Kepler's law of planetary motion is only strictly true for idealized systems with only two massive bodies. But the solar system is a many-bodied system with 8 planets, multiple moons around some of those planets, millions of small asteroids and icy bodies, and probably trillions of smaller debris, including meteorites and comets. So how do we address this multi-body problem? The simplest case is to define the orbit of a small body in the combined gravitational field of two larger objects orbiting each other. Some examples of this type of problem include a spacecraft in the Earth-Moon system, an asteroid orbiting the Sun near Jupiter, a comet passing by an inner planet on its parabolic orbit around the Sun. A formal solution to these types of problems, which are known as the three-body problem, was proposed by French mathematician and physicist Joseph Louis Lagrange. He showed that there were at least some solutions to the three-body problem if we restricted the three bodies to move in the same plane and assumed that the mass of one of them was so small that it was almost negligible, like the position of a satellite orbiting between Earth and the Moon. In his solution, the three bodies moved together, always maintaining the same positions relative to each other. Lagrange identified 5 islands of equilibrium that orbit in lockstep with the two main bodies. These are known as the Lagrange points, labeled L1 through L5. L4 and L5 are stable and can have objects trapped in stable orbits on those locations. L1 through L3 are unstable, and objects at these points are easily nudged out of their orbits and drift away. The Trojan asteroids of Jupiter are examples of objects trapped in stable orbits at the L4 and L5 Lagrange points. These are two families of asteroids that follow and lead Jupiter around the Sun as part of the Sun-Jupiter system. Trojan asteroids are those that follow an object at the L5 stable Lagrange point. In this case, the Trojans are following Jupiter at the L5 position. Greek asteroids are those that lead the object in the also stable L4 Lagrange point. A third family of asteroids can be seen here. Those are Hilda asteroids, which move in the elliptical orbits so that they are located opposite Jupiter at the position L3 and ahead or behind Jupiter at the L4 and L5 positions. To a first approximation, the orbits of most objects around the Sun are simple two-body Keplerian orbits. The solar system today is mostly empty, with large distances between big objects. Since the gravitational force gets weaker at the inverse square of the distance between objects, the gravitational pull from most solar system bodies are typically small compared to the Sun's gravity. Close encounters might disrupt the balance and create strong temporary gravitational pull. One example of those gravitational interactions are long-range perturbations. These are long-range interactions between two massive bodies orbiting the Sun. The extra object-to-object gravitational forces accelerate the bodies relative to their Keplerian orbits, with stronger effects when the objects are closer, lined up at opposition. Long-range perturbations cause a massive body to be affected by the gravity of another object. One classic case of long-range perturbations was the discovery of Neptune based exclusively on orbital perturbations on Uranus. After Uranus was discovered in 1781, measurements of its orbital path show systematic discrepancies between its predicted and actual position in the sky. Astronomers noticed that Uranus was accelerating in its orbit because of the combined gravity of one or more massive objects in the solar system. But adding the perturbations from the other known planets wasn't enough to explain the discrepancy. The extra acceleration was from the gravity of an 8th unknown massive planet orbiting somewhere beyond Saturn. Two astronomers, Leverrier in France and Adams in England, used the orbital changes in the motions of Uranus to calculate where this hidden planet should be. With the calculations on hand, Neptune was easily found on September 1846 by astronomers at the Berlin Observatory. Another type of gravitational interactions are the so-called close encounters. Close encounters between objects have much stronger effects than long-range perturbations because the distance between objects is small. These close encounters can dramatically alter the orbits of one or both bodies. Smaller objects are more strongly affected by close encounters than large bodies. As an example, imagine an incoming comet on a large elliptical or near parabolic orbit with a very long period approaching the Sun. The dashed path is the orbit the comet would follow if it had no Jupiter encounter. Notice that the orbital period is very large. But because of the presence of Jupiter, the comet is driven into a smaller elliptical orbit after a close gravitational encounter with the large gas giant. Here are both paths showing how the original large parabolical orbit ends up into a small elliptical orbit after the close encounter between the comet and Jupiter. Close encounters are also used as a gravitational slingshot to accelerate space probes and other spacecraft. In this example, a spacecraft catches up with Jupiter from behind and is accelerated by Jupiter's strong gravity. This, combined with Jupiter's orbital motion, gives the spacecraft a boost in speed, slinging it into the outer solar system. This is much more energy efficient than having to carry a very heavy payload of fuel to rocket the spacecraft to those high speeds. This gravitational slingshot was used by all outer solar system explorers, Voyager 1 and 2, Pioneer 10 and 11, Cassini, and New Horizons. Here is the Cassini gravity-assisted trajectory to Saturn. Boosts from Venus, Earth, and Jupiter were used to get Cassini to Saturn with minimal use of fuel. The reverse process is also true. If the close encounter occurs with the spacecraft getting in front of the planet, it can be used to take energy from the spacecraft, dropping it deeper into the inner solar system. This was done for the Messenger spacecraft, which traveled to Mercury, as you can see in this image. Another example of gravitational interactions are orbital resonances. They occur when orbiting bodies exert regular, periodic gravitational influence on each other, usually because their orbital periods are related by a ratio of small integers. Most commonly, this relationship is found for a pair of objects. Resonances are named for the number of orbits completed by each body in the pair. The first number is the number of orbits completed by the body being most perturbed. The second number is the number of orbits completed in the same time by the body causing most perturbation. One example is Pluto's 2-3 orbital resonance with Neptune, which means Pluto completes 2 orbits for every 3 orbits of Neptune. There are many examples of orbital resonance in the solar system. The 3 inner Galilean moons, Io, Europa, and Ganymede are in a 4-to-1 orbital resonance with each other. For every one orbit completed by Ganymede, Europa completes 2 orbits and Io completes 4. Another example are the 2 Neptunian moons, Naiad and Thalassa, which are the closest moons to Neptune. They are able to share space without colliding because they are locked into an unusual orbital resonance. Though their orbits are only about 1,800 kilometers apart, the 2 moons never get that close to each other. That's because Naiad's orbit is tilted. It travels faster than Thalassa, and when the 2 pass each other, they're always about 3,500 kilometers apart. The solar system is not a static clockwork that moves exactly the same forever. The dynamical state of the solar system changes over time as the planets interact through their mutual gravitation. Close encounters and resonances amplify these changes by rearranging orbits, destabilizing small body orbits, and even depopulating some orbits. Some resonances are stable, and objects swept into them can form distinct dynamical families of objects. All of these effects have helped shape the solar system over its long history. In summary, we have learned that the solar system is a multi-body system. And although most orbits around the Sun are simple 2-body Keplerian orbits, there are situations in which more than 2 bodies interact and affect each other. The orbit of a small body in the combined gravitational field of 2 large bodies orbiting each other is explained by the Lagrange points. Another example of gravitational interactions include long-range perturbations between massive bodies during closest approach, which allowed for the calculation of Neptune's position before it was discovered. Close encounters between objects have much stronger effects and can dramatically alter the orbit of one or both bodies. Close encounters are used to slingshot probes and spacecraft into extrasolar trajectories. Orbital resonances are regular and periodic gravitational influences between celestial bodies. There are many examples of orbital resonances in the solar system. Thank you for watching, and I see you in the next video.